In this video, we can discuss the theorems 5.717 onwards. 17 theorem 5.17 contains three statements. We start with the first one. If we start a non-zero ideal of O, you need to prove that this has only finite number of devices. We know that a result if D divides A, if and only if D contains A. This is the characterization of the divisibility of ideals. So if A is any non-zero ideal, then we write A as a product of prime ideals first. Then we can say that using this result, whenever we consider an divisor of A, we can say that D divides A. That is equal to P1 etc. PR. Okay, D divides this product. Okay, so we can say that every prime divisor of D is a divisor of this product. That is, if D can be written as Q1 etc. Q K, we can say that each Qi divides D and hence divides this product P1, P2 etc. PR. So we can say that Qi divides sum of this Pj. So we can say that these Qi's are nothing but Pj, because these are prime ideals. Every prime ideal is a maximal ideal as well. So this Qi is sum of Pj. So we can say that this D is nothing but D can be written as some Pn1, Pn2 etc. Pnk. Okay, so this shows that every divisor of A takes the form Pn1, Pn2 etc. Pnk. This Pn1 is nothing but one of these Pj's. So the only possible such product, okay, this is the product of ideals taken from this ideals P1, P2 etc. these prime ideals. So this product is always finite because this product is finite. We know that every for non-zero ideal A, the prime factorization is unique. So this product is unique. So this R is a finite number. So from these factors we can construct this D. So every divisor takes this form. So these forms are finite. So every divisor is a finite in number. Now we can put the second statement. A non-zero rational integer belongs to only a finite number of ideals of O. So we start with a non-zero rational integer, that is 0 not equal to an integer D belongs to Z. Okay, we need to prove that this D belongs to a finite number of ideals. So suppose D belongs to an ideal A, we can say that ideal generated by D is also contained in A. This shows that A divides ideal generated by D. Okay, so A is the divisor of D. But we know that means whenever D belongs to any ideal, then that ideal is always a divisor of A. We know that divisor by part A, we can say that this divisor, the possibility of the divisor is finite. So this A is choices of A. Okay, so choices of this A is finite because divisors are finite. So we can say that D belongs to a finite number of ideals A. So this proves B. Now we can prove C part. Only finitely many ideals of O have given no. Okay, that is, if we start with a positive integer n belongs to n, we need to find out the number of ideals. Is it finite or infinite? That contains this n. Okay, whenever n belongs to an ideal A, we can say that our assumption is n is the norm of A. Okay, so we need to find out the ideals A. We need to find A with norm A. Norm A is equal to n. We need to find out the ideals of this form. Okay, norm of A is n. We know that by theorem 5.14b, n is always, norm is always an element of A. So this shows that A contains ideal generated by n. Okay, so A divides n. So we can say that number of devices is finite, so the choices of such A is finite. So this proves the choices of such A is finite because the devices of any ideal is finite. So this n is contained in only a finitely many ideals. Okay, so the for n belongs to n, the number of ideals for which this n is a norm is always finite. Now we are going to prove the important theorem of this chapter 5. Before that, we will prove a lemma 5.19. If A and B are two non-zero ideal of O, then we can find an alpha belongs to A such that alpha A inverse plus B is always equal to O. Okay, so we need to prove for any two ideals, non-zero ideals, A and B, we can find an element alpha in one ideal such that alpha into A inverse. A inverse is a fractional ideal. Of course, alpha A inverse is also a fractional ideal plus B is equal to O. In fact, this alpha, if alpha belongs to A, then this not only a fractional ideal, this will be a ideal itself. Okay, because if we choose an alpha belongs to A, we have A divides alpha, or equivalently A divides ideal generated by alpha. This is the meaning of this A divides alpha. Therefore, what is the meaning of this? This means A contains ideal generated by alpha. Okay, then ideal generated by alpha is contained in A implies by multiplying A both sides with A inverse, we can write ideal generated by alpha into A inverse is contained in A inverse. Okay, so this is equal to O because this is the inverse of the ideal. So this product, this fractional ideal is always contained in O if and only if this is an ideal. Okay, whenever a fractional ideal is contained in O, then it is not only a fractional ideal, it is an ideal. So we can say that if alpha belongs to A, then this is always an ideal. Hence, this is the sum of two ideals. Sum of two ideals is defined as the greatest common divisor. Okay, so alpha A inverse and beta are ideals. Then the sum is always a greatest common divisor. That follows some kind of inclusion by the definition of the GCD. Now, once you prove alpha A inverse plus Pi equal to O, you can easily get alpha A inverse plus B is equal to O. Okay, because if you write this B is equal to P1, P2, etc., P say R, then you can, or of course there can be some powers also. So alpha A inverse plus P1 into etc. alpha A inverse plus P2 etc. PR is equal to O. Once you prove this result, you can write this product is equal to O into etc. O, that is equal to O itself. Okay, now what is this product? This product O can be written as this product is alpha A inverse. I start with this O is equal to this one, and product is alpha A inverse into alpha A inverse into etc. R times plus something into alpha A inverse plus etc. plus last time will be P1, P2, etc. PR. That means when you multiply all this, you can write this product as this much term plus P1, P2, etc. PR. The last term is always B, and all other term contains alpha A inverse. Okay, so this product is always contained in alpha inverse, and this is always contained in alpha inverse because alpha inverse is an ideal. So this is always contained in alpha A inverse plus B. Okay, so O is contained in this means O is equal to alpha A inverse plus B. Okay, because this is always an ideal of this is GCD of these two ideals. So whenever O is contained in this, the reverse inclusion is very trivial. So O can be written as this one. Okay, so once you therefore we have to prove that alpha A inverse plus Pi equal to O, or P of P1, P2, etc. Pr are the distinct prime ideals dividing B. If there are some powers of this, then you can use that much factors on this product. Okay, if there are P1 square, then you can write it as P1 alpha A inverse plus P1 into alpha A inverse plus P1 two times. Okay, you can write it two times. So we need not bother about the powers of P1, P2, Pr. We need to consider only distinct prime ideals dividing this B. So using this, we will prove this result first. Okay, for that we start with Pi does not divides alpha A inverse. Whenever this happens, we can say that an element beta belongs to does not belongs to Pi, but beta will be an element of alpha A inverse. So we can say that this Pi plus alpha A inverse properly contains Pi. Okay, so this implies Pi alpha A inverse plus Pi is equal to O, because Pi is the maximal ideal. So whenever this happens, Pi does not divide, so divides alpha A inverse. Meaning of this is Pi is not Pi does not contain this alpha A inverse. Okay, this means that there exists at least one element beta belongs to this one which is not in Pi. That means when you consider this sum, that will be properly contains this Pi. Okay, since Pi is maximal, the only possible ideal containing this properly containing this Pi is O. So then this result follows. Okay, so we need to prove that Pi does not divide alpha A inverse in order to get this one. So it is sufficient to choose an alpha from A minus API. This is set minus for all I equal to 1, 2, 3, etc. R. That is, whenever we choose an alpha from this, obviously this alpha will be an element of A, and alpha does not belong to API. Okay, this implies alpha A inverse is not contained in Pi by multiplying with A inverse on both sides. So once you choose an alpha such that alpha is an element of A minus API for all I equal to 1, 2, 3, etc. R, we are done. Okay, so the first case is very trivial. If R is equal to 1, then we can easily get an element from A which is not in API or AP1 if R is equal to 1, because whenever we know that A equal to AP1, I'll choose I is equal to 1 here, R is equal to 1 here, so it contains only one prime ideal P1. So if this happens, this implies P1 will be O. Okay, this is a contradiction, so this never happens. So we have A not equal to API, then we can choose an element A which is not in API. So that is very trivial. When R is equal to 1, the result follows. For R greater than 1, we let AI as AP1, AP2, etc. API minus 1, API, PI plus 1, etc. PR. We remove that PI from this product. One thing we need to remember is this need not be B. Okay, this is the distinct prime divisors of B. By the case R equal to 1, we can choose if we can say that A1 minus A1 not equal to A1 P1. So we can easily choose an element alpha 1 from this. Similarly, we can choose alpha 2 from A2 minus A2 P2, because these two ideals never be equal. So we can choose for each I, for I equal to 1 to 3, etc. R, we can choose alpha I. Okay, using this alpha I, we write alpha is equal to alpha 1 plus alpha 2 plus etc. alpha R. This alpha is going to be the required element in A minus API for all I. So we defined alpha. Clearly this is an element of A. Okay, because the alpha is element of AI. Okay, from the choice of this alpha I, that is an element of AI, and AI is always contained in A, because AI is the product of this. We know that whenever we consider two product AB, that is always contained in A and B as well. Okay, so product is always contained in both of these ideals. So this product is always contained in A, P1, etc. Okay, so in particular alpha is belongs to PI, AII, that is contained in A. So alpha is always an element of A because each element alpha 1, alpha 2, etc. alpha R is an element of A. Suppose if possible alpha belongs to API. Okay, we need to prove that alpha is not an element of API. Whenever alpha belongs to API for some I, we write that corresponding, suppose alpha belongs to some AP3, then we write alpha 3 is equal to. Okay, so if whenever alpha belongs to API, if j not equal to I, we can say that if this is the case, alpha belongs to AP3, then we can write alpha 3 as alpha minus, from this alpha minus alpha 1 minus alpha 2. Okay, if suppose there exist only three elements, so if you write this alpha 3 in this manner, we can say that our assumption is alpha belongs to AP3 and this alpha 1 is also belongs to AP3 and all these terms belongs to AP3. Okay, because alpha 1 comes from this alpha 1 is an element of A1. Okay, and what is A1? A1 is nothing but A into P2, P3, etc. Or suppose we have only three ideas, so this is A P2, P3. Okay, so we can say that this alpha 1 is an element of AP3 because A1 contains A and P3. Now if we consider alpha 2 comes from A2, then A2 is nothing but A P1, P3. Okay, then again this alpha 2 is a member of A into P3. Okay, so all these elements can be rest of the elements. If alpha belongs to AP3, then we remove that alpha or rewrite alpha 3 is equal to alpha minus of those terms, and all those terms are elements of AP3. Okay, so this is what we have written here. If j not equal to I, we write alpha is equal to j not equal to I, we have alpha j belongs to API. Okay, so alpha I can be written as alpha minus alpha 1 minus etc. We remove alpha I from the right side and transpose to this left side, then these all are elements of API. Clear? So this shows that alpha is a member of API. That means API divides ideal generated by alpha I. On the other hand, we can say that alpha I this AI divides alpha I. Okay, this is the selection of this alpha I. This is because of the selection of this alpha I. Alpha is a member of AI minus AI PI. So alpha is always a member of AI. So AI divides ideal generated by alpha I. So we have API divides alpha I and AI divides alpha I. What is the meaning of that? Alpha I, ideal generated by alpha I, can be written as API is a factor. That means API into some C. Now we have alpha I can also be written as AI into some D. What is AI? AI is A into P1 into etc. Pi minus 1 into Pi plus 1 etc. PR into D. This is AI. So AI into D. So from this you can say that Pi divides this one. Okay, so Pi divides this means Pi divides this as well. Okay, Pi divides this means Pi divides this product. Then we can say that Pi divides D. Okay, suppose this our assumption is A has prime factors Q1, Q2, etc. QR, Q, say some QK, and we have Pi here and C here. Okay, so whenever Pi divides this factor, we can say that Pi divides this product, that is Pi divides Q1 etc. QK, P1 etc. Pi minus 1, Pi plus 1, PR, D. So this implies Pi divides D. Okay, Pi divides D means Pi into some E is equal to D, or D can be written as, or Pi is a factor of D, so Pi D can be written as Pi into E. Now this can be rewritten as alpha I equal to AI into Di can be written as again Pi into E. Now we can say that AI Pi divides this. Okay, AI Pi divides alpha I means alpha is a member of this. Okay, this is a contradiction because we have chosen this alpha I from AI minus API. Okay, so we can say that this alpha belongs to API for some I is not possible. So alpha does not belongs to API for all I is equal to 1 to the etc. R. This implies alpha A inverse is not contained in Pi. Okay? So not contained in Pi. So this proves the theorem, the lemma 5.19. We have another possibilities here. If this Qi, one of these Qi is Pi, then we can takes the form, A takes this alpha I takes the form alpha I can be written as if some, suppose this Q is Q1 is some P1, so this P1 into Q2 into etc. Q K into again suppose our Pi is this P1 into C. If this is the case, we can start with Pi square. Okay, so Pi square divides this. Yeah, then Pi square should divide the second term as the second form as well. So Pi square P1, I'll take this Pi is P1. P1 square divides this, then P1 square divides alpha I. Alpha is AI D here. Okay, so AI can be written as A into P1 P2 etc. A can be written as P1 Q2 etc. QK, and we have P2 P3 etc. I take this Pi is P1, so I have to remove that P1 from AI, or this is A1 as well. So etc. P R into D. Okay, in this case we can cancel one Pi from this A part, then we can again get P1 divides this. Okay, then this P1 should divide D because there is no other P1 factor here. So this one P1 should divide this D. Again we can get this form, P1 or Pi divides D. Then we have D can be written as P1 into E. Okay, so then result follows. So there is no harm by assuming this Q1 Q2 QK are independent of this P1 P2 etc. PR. So this proves even if there is such possibility, the result follows.